Hello students, in today's lecture we'll learn about different physical properties of carboxylic acids and about acidic nature of carboxylic acids. Let's start with physical properties. Now this part you need to by heart. These are all facts. Aliphatic carboxylic acids. What are aliphatic hydroxylic acids? RCOH type of carboxylic acids. Up to 9 carbon atoms are colorless liquids and they have unpleasant odor. Higher carboxylic acids are wax-like solids. They have low volatility. As volatility is lesser, obviously they will be odorless. Now in the case of carboxylic acids, there is extensive intermolecular hydrogen bonding. So the molecular association will be very high. As a result, their boiling points are very high as compared to aldehydes, ketones and alcohols of comparable molecular masses. The hydrogen bonding is so strong that it is not broken even in vapor stage. Also try to understand, these carboxylic acids exist as a dimer. Keep this in mind. They exist as a dimer. This property will help you to solve the problems of colligative property part from paper 1. Carboxylic acids exist as a dimer in vapor phase as well as in aprotic solvents. In the next slide, I have shown the structure of dimer. Look at the screen. This carbonyl bond is polar because oxygen is more electronegative than carbon. So oxygen will be delta minus and carbon will be delta plus. Similarly, in this OH bond, oxygen is more electronegative than hydrogen. So hydrogen will be delta plus part, oxygen will be delta minus part. Similarly, in the another molecule. This is how the charge separation will happen. So hydrogen of OH of one molecule can form hydrogen bond with oxygen of carbonyl of another molecule. As a result, there will be intramolecular hydrogen bonding taking place. So it exists as a dimer in vapor phase as well as in aprotic solvents. Up to carbon number 4, carboxylic acids are miscible with water and their miscibility is because of formation of hydrogen bonds with molecule of water. But as the number of carbon atoms go on increasing, that means as the size of R increases, what happens? The size of hydrophobic part is increasing. Hydrophobic part is increasing, right? So its solubility in water will go on decreasing. Carboxylic acids will be soluble in organic solvents like benzene, ether, alcohol. You know the rule, like dissolves like. Now we'll discuss the acidity of carboxylic acids. Carboxylic acids react with active metals to form corresponding metal carboxylate salts along with evolution of hydrogen gas. They react with alkalis to form salt and water. Carboxylic acid will give proton, base will give OH minus ion to give water, and sodium carboxylate salt will be obtained. Carboxylic acids are strong acids, so they can even react with weaker bases like sodium bicarbonate. Other acids like phenols, which are weak acids, do not react with NaHCO3. So this sodium bicarbonate test, the reaction with sodium bicarbonate or sodium carbonate is used to distinguish between phenols and carboxylic acids. Phenols cannot react with weak bases like NaHCO3, but carboxylic acids being strong can react even with weaker bases like carbonates and bicarbonates. In this case, sodium carboxylate salt will be formed along with brisk effervescence due to evolution of carbon dioxide gas, and the solution will turn colorless because sodium salts are soluble in water. So what will be the observation for the reaction? Brisk effervescence along with formation of colorless solution, and phenols cannot give this reaction. It dissociates in water to give resonance stabilized carboxylate ions and hydronium ion. When water is a Lewis base, it will take up the proton from carboxylic acid, and this OH bond will break on oxygen. So we will be getting a carboxylate ion which is stabilized due to plus M effect, due to resonance effect, and water taking a proton will form hydronium ion. Okay, we'll rewrite that reaction again. RCOOH reacts with water, then equilibrium is set up to form RCOO minus ion, carboxylate ion and hydronium ion. Greater is the acidity of this RCOH, greater will be the concentration of dissociated carboxylate ion and hydronium ion. Now, we'll write down the equation for equilibrium constant. Equilibrium constant will be molar concentration of carboxylate ion into molar concentration of hydronium ion divided by molar concentration of undissociated carboxylic acid into molar concentration of water. Now I'm keeping the water term on the left hand side. As we are taking water in large excess, the concentration of water can be considered as a constant. So, product of two constants will be a new constant called as Ka, which is acid dissociation constant. So, acid dissociation constant is nothing but molar concentration of carboxylate ion into molar concentration of hydronium ion divided by molar concentration of undissociated acid. So, greater is the value of Ka. Greater will be the concentration of dissociated part. That is, greater will be the acidity. There is one more term called as pK, which is nothing but minus log of Ka. So, it is very obvious as the acidity is greater, Ka value will be greater and its minus log will be lower. So, greater is the acidity. Keep this in mind. Greater is the acidity. Greater is the Ka value. Lower will be its pKa value. Now we have already discussed this part. Electron withdrawing group when is present on R of carboxylic acid, it stabilizes the carboxylate ion. Carboxylate ion has a negative charge. If electron withdrawing group is present, this negative charge will be spread over more number of atoms. As a result, the ion will be stabilized. So EWG, electron withdrawing group, stabilizes the carbon ion. As a result, it enhances the acidity. Electron donating group will increase the negative charge. So it will increase the reactivity of that anion. As a result, acidic strength will decrease. So electron withdrawing groups increase the acidity, electron donating groups decrease the acidity.